In this video, we're going to look at organizing and displaying quantitative data. So remember, quantitative data is data which is numeric in nature, and it has to have two properties, and that is that it has units and that we can do meaningful calculations with it. So in this example, we have SAT scores. So SAT scores are numeric. They have units which are just points, and then we can do meaningful calculations with them. So if you have one SAT score and then you take the test again, we can subtract those two to see what your increase in your score is. So that's what we mean when we're talking about a meaningful calculation. So the first thing we're going to look at is what do we do when we want to organize quantitative data? So remember, the first thing that we do is we collect data and then we organize it, which basically means that we put it into a table. So we can make a frequency table. So the frequency table would be using this column here. So we're just going to list each of our score ranges and then the counts. We can do a relative frequency table. So here we're going to list each of our score ranges and then the percent or the proportion of values that are falling in that range. And then we can do a cumulative relative frequency table, which is going to list the scores and then the percent of the data up to and including that score range. These score ranges are referred to as classes or bins. You'll see both words used sort of interchangeably, so you should probably get used to hearing both of them. So your classes or bins should be equal in size, and we should have 5 to 20 classes or bins. So you can see this table has 14 of them, so that's within our range of 5 to 20. Now, as long as you're in the range of 5 to 20, that is fine. There's no rule about exactly how many that you have to have. So remember, frequencies are just counts. Relative frequencies we would get by taking each of the counts and dividing by the total. The cumulative relative frequency, we would add up all of the counts up to and including that bin or class and then divide by the total. So your cumulative relative frequency should always end with 1 because then you're dealing with 100% of your data. These relative frequencies and cumulative relative frequencies can be in the decimal form or they could be in percent form. So once we've organized our data, the next thing we want to do is make a graph so we can display the data. And there are several different graphs that we can use here. We're going to start by looking at 3 of them, and we'll look at 2 more of them later. So the first thing is we want to make sure that we have quantitative data. So the data are values of a quantitative variable, and we know the unit. So we can have a histogram, which is similar to a bar graph, but a bar graph is for categorical data, and the histogram is for quantitative data. And then we can have a stem and a leaf plot. So remember, in the stem and leaf plot, you probably saw these in algebra. The numbers here are referred to as the stem, and this is the beginning of the number. And then the numbers over here are the leaves, and this is the end of the number. And we want to make sure that we have a key for our stem and leaf plot, and then we can also have a dot plot. So we're going to take a look at each of these individual graphs. So the first is the histogram. So the histogram uses the adjacent bars here to show the distribution of the value. Each bar represents the frequency. So over here on this one we have frequency, or this one is relative frequency of the values that fall in each of the intervals of values. A histogram is good when we have a large data set. So when we have thousands of data values or even 500 data values, a histogram is a good option for that. The boundaries on the x-axis include the left value but not the right value. So if we look at this very first bar here, this includes the 4 and it goes up to and including the cutoff that would be here. So in this case, they didn't really give us that cutoff, so we're going to talk a little bit about how we can get that cutoff. First, we're going to take a look at a little demo here to talk about how many bars we should have. So remember, we said when we're making the frequency table that we should have between 5 and 20 classes or bins, and the same goes for your histogram. You should have between 5 and 20 bars. So in this demo, you can see that we have a histogram with 14 bars, and then we can adjust the interval size here to see what happens. So if we take that interval size and we make it much, much smaller, then you can see that your histogram gets a little bit too cluttered for you to even be able to read very easily. So if we have too many bars, then it's just too difficult to read. If, on the other hand, we take our interval size and we make it really large, then we're not really getting the information that we need to be able to describe our data. So this is just not giving us enough information. So we want to be back in that range where we can get that between 5 and 20 bars. And then we can see a good description of our data. So from this, we can see that our the big chunk of our data is sort of in this range right here. And then we've got some values up here on the high end. We've got a couple of values on the low end. So this gives us a better picture. So remember, we're shooting between 5 and 20. If we come back to the graph here, you can see that this graph has a few more than 20. It has about 24, I think. And so sometimes you'll want to break the rules, so to speak, because it just works for your data set. So although your goal is between 5 and 20, there are situations where you can sort of go a little bit above the 20. If you have a situation where your data will work with exactly 4 intervals, then that might be acceptable too. Okay, so just being able to kind of read our data here, we want to be able to answer the data goes from where to where. So we want the boundaries of this data. So we can see my lower boundary is a 4, and then my upper boundary is right here. So remember, when we're dealing with these bars, the bars include the lower bound, the left bound, but not the upper bound. And then in this case, they didn't give us all those values, so we need to figure out what they are. So I'm just going to look here between 7 and 8, and I'm going to say 1, 2, 3, 4, 5. So there's 5 bars between 7 and 8. So that means that between 7 and 8, which is 1 unit, we are dividing that into 5 bars. So that's 1/5, which is 2/10. So then that tells me that this is 7.2, and this is 7.4, and this is 7.6, and then 7.8, and then 8. So then that means this ends here at 9.2. So remember, this last bar includes the 9, but it does not include the 9.2. If there was a data value that included 9.2, then we would have to have another bar here. So here we would say the data goes from 4 to 9.2. It includes the 4 because we always include the left endpoint, but we don't include the right endpoint. So it goes up to 9.2, but it doesn't include 9.2. The magnitudes of the tallest bar are between what 2 values? So my tallest bar is right here. So that's going to be between 7 and then the 7.2. And then again, remember, we're including the 7. So remember, we're going to include the 7. So the magnitudes are between 7, including the 7, and then up to 7.2, but we're not going to include the 7.2. And the approximate frequency of the tallest bar, so the frequency would be how high it goes. So we're just going to say that looks like it's about 200. So there's about 200 earthquakes who had magnitudes between 7 and 7.2. Okay, so my next graph that we're going to look at is the stem and leaf plot. So this shows quantitative data values in a way that sketches the distribution of the data. It shows each of the individual data values. So back here with the histogram, we don't see the individual data values. We just see the ranges that they fall into. Where with the stem and leaf plot, we can see actually every single data value. So this is suited for small to medium amounts of data. So if we have hundreds of data values, this is going to be too big and cluttered to be able to read very well. So this is something that we're going to use when we have a small to a moderate sort of data set. So a couple things here. Remember, these values here are my stems, and then these values are the leaves. These first 2 graphs are actually representing the same data set. This second graph here is called a split stem graph, and that's because you can see there's 2 5s and 2 6s and 2 7s and 2 8s. So for each number, we're just splitting the values, the first half of the values that are in the 50s and the second half of values in the 50s, the first half of values in the 60s, and then the second half of values in the 60s, etc. And this is just a personal choice. So leaves that are between 0 and 4, including 0 and 4, would go in the first line. So you can see in the 60s we've got 0s and 4s. Leaves of 5 through 9 would go in the second one. So in the 60s, the only leaf we have is 8, so it's in the second. It's in the second line of 6s. This last graph here is what we refer to as a back-to-back stem and leaf plot. So this is just a stem and leaf plot that's representing 2 sets of the data. So here you can see we have data, we have infant death rates by state, and these are divided into 2 regions of Northeast and Midwest, and then the South and West. So one of them is typical with the stems in the middle. So remember, these are still my stems. And then I've got leaves over here representing the Northeast and Midwest, and then I've got another set of leaves over here. So you just have to remember you're reading these backwards. So this value here starts with the 8 and then with the 6, and then come down here. Remember, always pay attention to your key. So this shows us that 3/8 really means 3.8, so there's a decimal point in there, and then deaths per 1,000 live birth. So this value right here would be 8.6 deaths per 1,000 live births. This value here would be 4.8 deaths per 1,000 live births. So always make sure that you pay attention to your key, so you know what your units are, and you know if you have decimal points or if you need to multiply by 100 or something like that. All right, so if we look specifically at this stem plot, so this is representing pulse rate. So here we can see that 5/6 just means 56, so we don't have to do any sort of multiplication to the value. And then this also tells us our unit, which was beats per minute. So what is the lowest pulse rate? So I'm going to look for my lowest stem, which is in the 50s. And then this is 56, so 56 beats per minute. What's the highest pulse rate? So the highest pulse rate is going to come from here. So remember, I'm going to take this number and then I'm going to put this number at the end of it. So 884, so 84 beats per minute. And then this is asking us how many people had a pulse rate of 76. So I want to find the 7s, and then here are all of the 6s, and there's 1, 2, 3, 4 of them. So 4 people had a pulse rate of 76. All right, and then the last graph that we're looking at here is a dot plot. So the dot plot has a number line for the x-axis. So you want to have just your horizontal line, and then you want to put your numbers on there, and then note your units. And then again, this is well suited for small to moderate data sets. If we have hundreds or thousands of data values, we don't want to be making dots for every single one of those. So essentially you just draw your number line and then you put a dot above the data value for each of your values that are in your data set. So here we're looking at the fuel economy for a random sample of vehicles from the year 2015. So how many data values are in this set? So in order to answer this question, we're just going to count the dots. So I have 16 data values. The data range from, so now I just want to find the smallest and largest data values on the number line here. So we have a data value of 16 and we have a data value of 40. So the data range from 16 miles per gallon to 40 miles per gallon. So please remember here, when we're starting to work with this numeric data, that we need to always answer our questions in the context of the problem, and so we want to use units. What data value has the highest frequency? So here I can see that this data value has the most dots above it. So it's similar to the histogram. You can just see which one has the highest bar, but here we're just looking for the dots. The dots kind of simulate the bar. So that's between 30 and 32, which is obviously going to be 31, so 31 miles per gallon. And then how many vehicles have 32 miles per gallon for their fuel efficiency? So here I'm going to look at the 32 and I can see that there are 2 dots above it, so 2 vehicles.